What's up, everybody? Today, we're going to go over some of the mathematics behind linear regression. I'm going to do this through the lens of a specific small example so that we can see some of the more complex mathematics in action. In order to do that, I'm going to use this notebook to illustrate some of the ideas with Python code. Okay, so let's get started. We're going to start, as we commonly do, by importing some of the necessary libraries. So the first thing I'm going to do is import NumPy, which is a linear algebra module for Python. And the second thing I'm going to do is actually import Seaborn, which is a Python module built on Matplotlib that I like a little bit better than Matplotlib. And the last thing I'm going to do in this cell is actually convert to dark mode because I have dark mode in my IDE. So let's go ahead and run that. Okay, so let's get started with our example. The first thing I'm going to do is create a bunch of data points. That is the independent variables. So let's go ahead and do that. So I'm going to just create a bunch of random points. So it's going to be uniformly distributed. The lower bound I'm going to have for my uniform distribution is 0. The upper bound I'll just choose 1, and I'll make 1,000 points. So there is my data, and let's just print the shape just to make sure it did what we expected it to do. So we get 1,000 data points. The next thing I'm going to do is create my target variable, that is the y variable. In order to do this, I'm going to actually do something like this, plus 3. So I'm going to assume that the target variable is roughly 2 times x plus 3. But if we assume it's exactly that, it's not too interested. So actually GitHub Copilot exactly suggestion what I want to do, which is to add some random noise. Now this is the addition of some random noise. The first parameter is the mean. So basically on average, the random noise will be adding 0, but there'll be some variation, which we'll talk about in a second. Now let's go ahead and look at a picture of what this will look like. So let's plot x to y. And let's also plot the line that is given by 2x plus 3. So let's ask GitHub Copilot to do that for us. And it goes ahead and does that. One thing I'm going to do here is just set underscore equal to that so it doesn't print out extra text that we don't need to see. Now that all situated, we can now see the plot. And we're getting some warnings here, future warnings. So why I'm getting a warning is because I should put these things as keyword arguments. Like this, and y equals this. But one thing I'm going to do is plot the line as a red line. And then let's try that again. Perfect. So now it gives it exactly how I wanted it. And there we go. So we can see that the target variable, the y variable, is almost on this line, but oscillates a bit up and down from that line. So here I'm going to explain a bit more of this random noise. So let's actually call a variable random noise. And let's just say it's equal to np.random.normal, like we did above. So 0, 1, and 1,000, like above. And let's just do a histogram. So let's do that. That's almost perfect, except for, again, we should use the keyword argument data. And we can see that the random noise looks like this as a histogram. So you can see it's mostly concentrated around 0, but it kind of goes out to -1 and -2, sometimes. And there's one thing that's a little bit different than the noise I did above, so let's actually go ahead and fix that. So you can see the noise I did above has this parameter is 0.1, that's the standard deviation. But here I used the 1 right here. So let's change that to 0.1, and that'll have the effect of shrinking the graph a bit. So let's have a look. And you can see the 1 is changed to 0.1. You can see this is not perfectly normally distributed if you know what the normal distribution looks like. Well, that's because the data set's a bit small and the graph in error. So if we make it bigger, it'll look a lot nicer. But anyway, so what we're seeing is that the random noise that we're adding is basically on average 0 with some oscillation about Sometimes it could be 0.1 or 0.2 or negative 0.1 or negative 0.2, but yeah, that's about how much the random noise is oscillating. And if we go back to the graph up above, we can see that a typical point lies within, 0.1 or 0.2 of the red line. So this is kind of matching up with the distribution here. So I want to go back to the definition of this target variable. And now we can see that we're basically assuming that the y variable is exactly equal to 2x plus 3 plus a little bit of random noise. Now this might look kind of contrived, but in fact this is the exact assumptions that you make when you try to apply linear regression. You assume that your target variable is exactly a linear function of x, in this case 2x plus 3, plus some random noise, like we did here. This is of course a contrived assumption for a lot of data sets that arise in practice. However, it gives us a firm theoretical baseline so that we can derive some theory and some guiding principles when applying linear regression. Now in practice, we're not going to have any idea what this 2 and this 3 is, because we're only going to have access to the data points. So the next natural question is, how would I figure out what this 2 and 3 are without knowing this beforehand? So let's go ahead and attack that problem. It turns out that for linear regression, there's a closed form solution, and that you can actually tell the computer to exactly solve for it. This is a very unique situation that doesn't appear in other machine learning algorithms, in which case you usually have to use an iterative algorithm to slowly find a closer approximation to the actual solution. With that in mind, let's go ahead and see how we would find the exact solution. So the first thing we're going to have to do is add an intercept column to x. So let's go ahead and do that. So let's query GitHub Copilot to do that. So add an intercept column to x as the first column. And it redefines the variable x, which I do not like to do, because in a notebook, if you start redefining variables in different cells, it can get confusing if you run them out of order by accident. So I'm going to make this a capital X and just see if it worked. So let's try x.shape. So it looks good, and let's see what it actually looks like. And we can see that we're adding a full column of 1s alongside our original data. Going back to the target variable, the 1s correspond to the intercept, and the next column corresponds to the multiplication by x. In fact, if I'm going to do this properly, it could be like this, because the intercept will be first, as I've written it, and then the solvent for the 2 will be the second variable. So let's go ahead and do that. So now that we have our x, we're actually only one line of code away from solving for these coefficients. So again, we're trying to find, right? So the goal is to find something close to 3, 2 as the solution, because 3 was the intercept and 2 was the slope. So let's go ahead and do this. So let's do beta equals, and it kind of gives a solution, and this actually is correct, but I'm going to do it a slightly better way, where I don't have to compute the inverse. So there's a function called solve, and yes, this one is what I want. So this turns out to be the least squares solution. So let's go ahead and print beta and see if it's close to what we thought it would be. And yes, it is quite close, 2.98 and 2.01. So again, this is an exact formula, and it gives the actual solution to beta. Now you might wonder, why is it not actually exactly 3.2? And we'll talk about that in a bit. But again, I wanted to warn you that this exact formula is not something that's common for most machine learning algorithms, and is actually very specific to linear regression. Now, it's a natural question to ask, why did we not get exactly 3, 2? And if we go up here, we notice that we do actually add some random noise to the target variable y. So we can't expect that the answer will be exactly 3, 2, and in fact, it should vary slightly based on the fluctuations of the random noise. But how does it actually fluctuate? And that's what we're going to talk about next. Okay, so I took everything we did above in terms of creating a target variable and then solving for beta and put it into a function. So let's go ahead and execute that. And now I'm actually going to execute this function many times. So let's go ahead and do that. So let's define a variable betas, and we're going to do this one exactly. So we're going to run this experiment. Let's do it 10,000 times, and we'll just have a list of betas. I'm going to keep the same x, but I'm going to keep generating different y's based on how this random normal distribution runs. So let's go ahead and do that. But before we do, since we don't use this I variable here, sometimes it's best practice to put an underscore instead of an I. So those 10,000 experiments only took 0.5 seconds, which is not too bad. And let's go ahead and plot the betas. So let's plot them as a scatter plot and see if GitHub Copilot can do that one. And I think that's gonna work. And look at this. So these are all the different betas that you get from generating different y's. Notice that 3 as the x-axis and then comma 2 as the y-axis is pretty much at the quote-unquote center of this ellipse type shape. Again, 3 corresponds to the intercept and 2 corresponds to the slope, which is exactly how the line that is used to create y is formed. So this picture gives us an idea of how the fluctuations in the random noise used to generate y actually affect the solution beta. So it turns out that the distribution of these betas is actually given by a multivariate normal distribution with mean 3, 2 and some complicated covariance matrix that we'll compute later. So first of all, we're using a multivariate normal distribution, which we'll talk about. But the only thing that we can kind of see is this 3, 2, which is actually exactly what we used to generate the data. That was the 3 was the intercept and 2 was the slope. And if we go to the graph here, we can see that again, 3, 2 is kind of at the center of these set of points. So that's actually something that's true in general. Whatever is used to generate your data, whatever vector, in this case it was 3, 2, this will be at the center of your distribution. So that'll be the average. So what I'm going to do next is actually show another way you could generate this similar distribution through this multivariate normal distribution. So let's actually do that. So we'll define sigma, and this will be np.lineage.inverse of this one. And this is exactly coming from this guy. And we'll multiply by the standard deviation, but we have to square it, because that's what it is in the formula. And let's just print sigma. And we can see that we do actually get a 2x2 matrix, which is exactly what we would need for a normal distribution that lies in the two-dimensional plane. Cool, so now let's generate points according to this normal distribution. Perfect, and it actually gives the mean here, which is 3, 2 and sigma. And let's print beta. Now first you'll see that for one sample, it's pretty close to this 3, 2. Now let's go ahead and actually generate many points using this methodology. So first let's create a variable betas from the simulation, and we'll use list comprehension as I suggested. And then let's go ahead and make a scatter plot. There we go, and let's see how it looks. And we can see we get almost the exact same picture. It's let's see, so the top is 2.04 and the bottom is 1.96. If we go over here, we get something very similar, 2.04, 1.96. And if we look left to right, 2.98 to 3.02, and we get something very similar here. So in conclusion, we create this target variable using a random method. This random method will in turn generate different betas that are going to be the solution to the least squares problem. These different betas are distributed, like in the picture here, and their mean is importantly going to be the same vector that's used to generate the data. So that's all I wanted to share with you today. I hope you enjoyed it. I do want to mention that I took the least squares solution as being the correct solution for granted, and that's something we could discuss in a future video. In any case, thanks for watching and have a good one.